Alright, so let's look at chapter number 7, which is finite impulse response filter design. As we discussed finite impulse response and infinite impulse response filters in the last chapter, finite impulse response filters are filters whose impulse response, of course, have finite number of terms. And on the other hand, IIR or infinite impulse response filters that we will study in the next chapter are filters that have infinite values of impulse responses. And the other difference between the two filters are, of course, from the difference equation. The difference equation of FIR filters, as we discussed for any other DSP systems in the initial chapters. The difference equation only has x and previous instances of x, that is input, but it does not have any previous instance of the output. On the other hand, IIR filters, they have previous instances of output, input, previous instances of input, anything can possible in the difference equation of IIR filters. So FIR filters, as we know, the generic equation, since it is only comprised of input and the previous instances of input, hence the difference equation, generic difference equation, is given by 7.1. You have k terms of input and the previous instances of input. And once you do, and now we're gonna assume that all the initial values are 0 for input and output both. Once you do the Z transform, once you take the Z transform of this 7.1, then of course you're going to get 7.2 equation, where the transfer function can be written for the FIR filter as B0 plus B1 Z inverse plus all the way up to BK Z to the power negative K. So if you write it down in terms of the positive powers of K's, then equation 7.3 represent that expression. So if the Z transform transfer function is given to you, then to identify if it is an FIR filter or IIR filter from the Z transform transfer function equation, you only have to look at the denominator. If all of the zeros, all of the poles are at Z is equal to 0. So this equation has k poles. So Z times Z times Z all the way, all the multiplication, such that you are multiplying k values of Z. And each value, of course, the pole represent Z is equal to 0. So you have k poles at Z is equal to 0, which is inside the unit circle. So that's one way to identify the FIR filter, that all poles will be at Z is equal to 0 inside the unit circle. And since all poles are inside the unit circle, that means FIR filter will always be stable. Always be stable. On the other hand, IIR filter can be stable or unstable. Of course, we want the filter to be stable, but if you don't design it carefully, then you can make it unstable by putting some of the poles outside the unit circle. But in this case, FIR filter will always be a stable filter. So first example, FIR filter expression is given to you, and we have to figure out the transfer function, filter length, coefficients, and impulse response. So transfer function, of course, you take the Z transform on both sides and then take the ratio of YZ over XZ to give the transfer function. And from here, of course, we can see that B0 is this, and B1 is this, and B2 is this. So these are three coefficients. And once you take the inverse, so if for impulse function, of course, XZ is equal to 1, so HZ will be equal to YZ. So when you take the inverse Z transform, keeping XZ is equal to 1, then you are going to get 0.1. So 0.1 is going to be 0.1 delta n, and 0.25 delta n minus 1 using the shift property, and then 0.2 delta n minus 2. So it has only three values because it's a finite impulse response system. It has value at n is equal to 0, n is equal to 1, and n is equal to 2. 0.1, 0.25, and 0.2 respectively. Okay, so let's look at how to design the FIR filter using Fourier transform design. So we are going to start with an ideal low pass filter. So this is an ideal low pass filter. Of course, don't look at the negative frequency, look at the positive frequency. This filter has the magnitude of 1, that they're not showing it, but this is 1 over here, and the normalized cutoff frequency is omega c. And of course, on the negative frequency side, you can see that negative omega c. And the filter response, of course, as we studied, the frequency response of any DSP system, it is periodic with the periodicity of 2 pi. So it is 1 period over here, from negative pi to pi, that is 2 pi. So we're gonna go ahead and we are going to h e j omega is a periodic function as we studied, so we can extend the frequency response as it is shown over here. So that's the periodicity that it is shown, which is one of the properties of h of e j omega as we discussed in the last chapter. So we can write down, since it's a periodic function, we can write down in terms of Fourier series, right? But this Fourier series is not in the time domain, it is in the frequency domain. So this is a complex Fourier series or exponential Fourier series, as we discussed in one of the earlier chapters when we were discussing DFT. And the coefficient Cn can be represented by this expression. Now the frequency omega naught here is 2 pi f naught, and f naught is the frequency, fundamental frequency, right? So we can also write down 2 pi over 1 time period t naught, and since this is the frequency domain response, right, 1 time period here is from negative pi to pi, that is 2 pi. So this, although we should not call it t naught because this is not the frequency scale, we can call it omega naught. That will be a better term over here, right? So instead of calling it t naught, let's call it omega naught, because again the frequency scale is normalized frequency omega. So omega naught is 1 time period or 1 frequency period on the scale of omega, and omega naught is equal to 1 period is equal to 2 pi. So you're gonna have the frequency omega naught 2 pi over 2 pi, which is equal to 1. So this omega naught is going to be 1 over here. And we replace c of n by h of n, that is the impulse response of the function, because when you are writing the Fourier series, then this is the time function and this is the frequency function, of course, right? So the frequency function is h of e j omega, which is the transfer function of the impulse response. So the time domain corresponding function is going to be h of n, which will be c of n. So that's going to be negative j, omega naught becomes 1, n omega. See, we replace the time by omega over here, right? Because our scale is omega. So we know that z is equal to e to the power j omega. So we're going to write down h of e j omega as h of z, and then h of e to the power negative j n omega as z to the power negative n from here. So h n z to the power negative n. And when you expand this, then you're gonna get h negative 2 z square plus h negative so on and so forth, h0 and this. So this is the transfer function of a non-causal FIR filter that we got from the Fourier series, Fourier transform. This is non-causal because you have z square, you have z1, stuff like that, right? Now if it is causal, remember it will always have the negative powers of 0 and the negative powers of 0. So this is a non-causal filter, and then we're gonna make a causal filter from this, as you will see pretty soon. So h of n from this equation, so remember we said that Cn is h of n, so h of n is equal to 1 over 2 pi integral from negative pi to pi h of e j omega e to the power j, and omega naught is equal to 1 n omega. So we're gonna replace the c of n by h of n. So h of n is this, right? And we can determine h of n for different values of n. N is equal to 0 is going to be, remember, h of ej omega, the magnitude is 1, so we're going to go ahead and replace that by 1, and then 1 is from negative omega c, which is the cutoff frequency on the normalized scale, to positive omega c. So we replace h of ej omega 1, and we put n is equal to 0 over here, ej omega n. So we're gonna get omega c over pi for h of n when n is equal to 0. And when n is not equal to 0, then we are going to get h of ej omega is, of course, is still 1, but then we're gonna get this function, and once you take the integral of this function and solve it, this is what you're going to get right here. So these are our coefficients of the transfer function, which is not the transfer function, sorry, for your transfer function, but that transfer function is the non-causal transfer function, right? So we have h of 0, this is h of 0, and then this is h of not equal to 0. So h of negative 1, positive 1, negative 2, positive 2, so on and so forth. Negative 1, positive 1, stuff like that. So these are the coefficient of right here, right? H of negative 2, h of negative 1, h of 0, h1, h2, so on and so forth. Now h of negative 2 and h of 2, they have the same value, they're symmetric, it's a symmetric function. H of negative 1, h of 1, same value. H of 0, of course, is a different value that you can see over here. It's a different value right here. But if you put any value of n, either positive or negative, this function is going to give you the same result, because sign of negative value is negative sign, and if you have a negative n, then of course denominator is going to be negative, so negative in the numerator and negative in the denominator will cancel each other. Likewise, if you're putting positive values, then it's going to be the same as negative over negative. Okay, so this function is called sinc function. Sinc function is basically sine of x over x. This is called sinc of x. So this function, although it is not written in terms of sinc function, but you can write this in terms of sinc function, and in terms of sinc function is going to be sinc omega c n, so we have to put omega c in the denominator. That means we'll have to multiply and divide by omega c. So omega c over pi sinc omega c n. If you want to write it down in terms of sinc function, then this is going to be what it is. This is how it's going to be written down. Now sinc function has this type of characteristic. So it basically oscillates like this. So this is the time domain characteristic of the sinc function. Now from this characteristics, you can see that you cannot really consider the ideal low pass filter. Since we are considering the ideal low pass filter, you cannot even consider the ideal low pass filter even theoretically, because the response is starting actually before n is equal to 0. It's a non-causal, remember. And non-causal really does not really exist, because if you do not really have any input arrived, the output should not arrive. So that means even theoretically, the time domain and communication systems, you discussed that when you're creating even analog filter and considering an ideal analog filter, the time domain response start before n is equal to 0. It's a sinc function, and that's why we say that even theoretically it is impossible to conceive an ideal filter response. And of course practical, you know that we don't have ideal filter response, although we can go close to ideal filter response if you start increasing the order of the filter, as you will see soon. Okay, so how to make this filter a causal filter? To make this filter a causal filter, basically what we do, we shift this function by whatever the length of the filter is. that means we multiply this function by z to the power negative, whatever the highest power of of z is. So let's say if this is your function, so the length of the function is 5 over here. Length means how many h's are there, values of h. So you have h negative 2, h negative 1, h0, h1, h2. So it's a length 5, or what we also call 5 tap filter. And the highest value of z is a square. So you multiply the whole equation by z to the power negative 2. So when you do z to the power negative 2, this is going to become 0. This is going to be negative 1. Then you have negative 2, negative 3, and negative 4. So this will come in the standard form of FIR filter equation. In other words, you are shifting this filter towards right. Remember, anytime you multiply difference equation by z to the power negative value, basically you're shifting the equation by that many time instances towards right. Anytime you multiply a difference equation by z to the positive value, you are shifting that difference equation by that many time instances towards left. So to make this filter causal, you basically have to shift the sequence h, which is the sinc function. You have to shift this sinc function towards right by whatever the value of n is. In other words, if you see over here, if the length of the filter is given by 2m plus 1, right? So length of the filter is taken as 2m plus 1. So if it's a filter length 5, like we discussed earlier, then m is equal to 2, right? M is equal to 2, and we saw that over here, right? M is equal to 2. So it is going from h of negative 2 z square, h of negative 1 z1, all the way up to h of 2 z negative 2. This has the length 5. So when you have length, and length will always be odd number. Remember that, always be odd number. You need to have symmetric values over here. If it is a square, that has to be negative 2, right? If it is cube, that has to be negative 3. And in that case, the length is going to be 7 if it is value cube, z cube. So length will always be an odd number. So again, to shift it, you multiply the whole sequence by z to the power negative m. Z to the power negative m. So if your non-causal filter is this hm zm plus h1 z1, so on and so forth, and observe we are taking hm over here and hm here because these two values are same, right? h1 and h1 will be same. So this is h of negative m, this is h of positive m, but both values are same. That's why they are showing h of m. So to shift this towards right, we're gonna multiply this whole thing by z to the power negative m. And when we do that, then the zm will be gone, and then the equation is going to look like this: hm minus 1 z negative 1 hm minus 2 all the way. So h of 0 will always have the coefficient z to the power negative m. Always have the coefficient z to the power negative m, always have the coefficient of h of 0, right? And when we use the standard variables b's, since we use b's for our causal filter, then b naught plus b1 z inverse plus b2 z negative 2, and b1 is going to be hm, b1 is going to be hm minus 1, b2 is equal to this and that. So you don't really have to change anything as far as manipulation is concerned for the values of h. So when you're shifting, basically whatever the first value is going to be the first coefficient is going to be the coefficient of z to the power 0, the second coefficient is going to be z to the power negative 1, and so on and so forth. Okay, now this is the low pass filter that we discussed. So the low pass filter impulse response for non-causal sequence is this. Now similarly, we can design high pass, band pass, band stop. We're not going to show it. Just the table 7.1 in the book is given to you to use the impulse response. Or so when we say the ideal impulse response for the causal filter, so first you are going to calculate these, and then you're going to shift that to get the causal response or causal components, which is b naught b1, which is pretty much the same as hm minus 1, so on and so forth. So high pass filter equation is this, band pass filter is this, and band stop filter is this. Observe that for n is equal to 0, each one has a different h of 0, and when it is not 0, then this is the equation for not 0, when n is equal to not 0. And remember, for negative values of n and positive values of n, it is the same value of h of n. So h of -7 and h of +7 will give you the same value, as you will see when you will evaluate it. So let's look at this example. We have to design an FIR low pass filter with filter length of 5, that is 5 taps, cutoff frequency 1 kHz, sampling frequency 8 kHz. So first we are going to determine what is the value of m, right? M is equal to 2. We're going to take the non-causal filter equation for the low pass filter that we derived also. For n is equal to 0, you have omega c, normalized frequency, cutoff frequency, over pi, and this. So first we're going to calculate what is the value of omega c from the value of fc that is given to us. So we are given the cutoff frequency in hertz. So omega c, as we discussed in the last chapter, is omega c times ts. So 2 pi fc, and ts is 1 over fs, 2 pi fc over fs, and fs is given to us 8 kilohertz, and fc is 1 kilohertz. So we're going to put that, and omega c will come out to be pi by 4 radians. So from that, pi by 4 radians, and using this equation right here, you are going to calculate h of 0, pi by 4 over pi, which will be 1 by 4 only, 0.25, which you can see over here. H of 0 is 0.25. And then you're going to go ahead and use this equation, and you're going to calculate for n is equal to -2, which will be equal to n is equal to +2, which will be this. When you put the numbers in, they are same. And then n is equal to -1, which will be the same as n is equal to 1, which is this. So this will be the response of non-causal filter. As you can see, the powers of these are positive. So this is non-causal filter. So you're going to go ahead and multiply this equation by z to the power -2, and then you're going to make it causal, right? So you multiply that by z to the power -2, shift it towards the right by -2 the time instances, or two time instances, and then your causal filter equation is this, where b0 is this, b1 is this, b2 is this, b3 is this, and b4 is this. Total length 5. Okay, when you have to draw the frequency response, like we did in chapter number 6, you put z is equal to e to the power j omega, right? Oops, e to the power j omega. And then for all z's, you're going to put e to the power j omega. Now again, if I ask you to show me the magnitude response expression and phase response expression, then remember, like we did in chapter number 6, you're going to apply Euler's identity, and then you are going to write e to the power j omega, or negative j omega, positive negative j omega, whatever you are using, as cosine omega plus minus j sine omega. And then you are going to take all the real numbers, put them on one side, and then plus j or minus j, whatever you have, and then all the imaginary number, put them on one side. And that is going to be your h of ej omega written in complex form with real part and imaginary part. So when you take the magnitude of that, you are going to take square root of the real part square plus square plus the imaginary part square without j. Remember, don't include j when you're calculating the magnitude. And when you have to take the phase of that, then arctan of imaginary part without j divided by real part. So if I ask you again, once again, to show me the response equation, magnitude and phase, you have to first convert this using the Euler's identity, and then show me those responses as we discussed in chapter number 6. I'm not showing you over here, but again, if I ask you, then you have to show me that. So what I did, I just went ahead and then I plotted these in MATLAB or Octave from these difference equation as we discussed in chapter number 6. So either you can use freq z function, or you can simply use the method that we discussed in chapter number 6, whichever way you want to do. So this is the magnitude response, and this is the phase response. Now observe these ripples, as we discussed towards the end of chapter number 6, and I showed you the ripples in the stop band and pass band. These are the ripples that you can see when you plot the response of the FIR filter or IR filter in the next chapter. Another example, in this the filter length is 7, so m is equal to 3, and we are designing what we're designing, band pass filter. So we're designing a band pass filter. So we take the equation of the band pass filter from table 7.1. Now in band pass filter you have the high frequency cutoff frequency and you have the low cutoff frequency, right? Omega L, omega H, and omega L. So you have to calculate both the cutoff frequencies, and in the question your lower cutoff frequency is given 7 kilohertz, your upper cutoff frequency is given 5 kilohertz, and upper cutoff frequency is given 7 kilohertz, and sampling frequency is given 20 kilohertz. Now remember, when you plot the frequency response, then you only have to plot up to what? Fs by 2, which is 10 kilohertz. So all the frequency response, the frequency response of your filter should be within 10 kilohertz, and it will be within 10 kilohertz since the upper cutoff frequency is 7 kilohertz. So it should not exceed 10 kilohertz. So it's going to be something like this, right? Now of course you will have some ripples over here, but up to 10 kilohertz this is going to be response. Now remember, if your Fs by 2 is such that this value or this value is greater than that, then you're not designing properly, because all the frequencies, remember, should be less than Fs by 2, which is the Nyquist frequency or fold-over frequency. And then the sampling frequency will simply be, according to Nyquist rate, double the amount of the highest frequency, which in this case has to be within Fs by 2. Okay, so first we're going to calculate omega H and omega L. We know FH and FAL. So we calculated those two things. Then we used the filter equation, response equation, non-causal, first calculated non-causal coefficients, and then multiplied that by z to the power -3 to calculate it causal coefficient. And then from there we plotted the magnitude response and phase response. So you don't really have much ripples over here in the pass band, but you can see the stop band ripple. And here I'm plotting, I think, about 100 points. You can plot more points as well. I was taking 100 points between 0 and pi. But you can take a 1000, usually you can do 2 to the power 10 or 1024 points. I think that will be a good idea. Although it's pretty smooth. Sometimes phase response, if you plot more points, phase response becomes better. Okay, example number 4 for high pass filter, length 49. So since we have length 49, I'm not going to show you all those values. Of course, these are too many values. I'm just going to go ahead and plot it. So length, oh, hold on, it's 49 or 99, which one I did, because I'm putting 99 over here. Could be 99, let's see. Yeah, I don't remember exactly what did I do, 49, 99, well, one of them. I have to go back and check. I believe I did 49, and then initially I was doing 99, but then I moved to 49. Anyways, so whichever, it doesn't really matter. If it is 99, then m is equal to 49. If it is 49, then m is equal to 28. No, 48 divided by 2 is 24. So m will be equal to, if it is 49, then it's 48 divided by 2, 24. So 2m plus 1 is equal to 49. So m is equal to, it will be equal to what, 24, 25, whatever is that. Alright, so I'm gonna go ahead and use the equation of FIR high pass filter, and then I'm gonna fix it in the notes though, but it's the same procedure. And then I'm gonna first calculate omega C, which come out to be pi by 4. And as I said, filter is just too long, so I'm not going to show you H values, but I'm going to go ahead and plot that. First calculate it in MATLAB, all the coefficients, and then plot that. So this is the magnitude response of the filter, and this is the magnitude response in decibel. So many times actually in the project as well, I guess I'm asking you to draw in decibel. I forgot if I am asking you or not, but there's a decibel response which is right here, 20 log 10 h of eg omega. So this is that, and this is the regular response. And as you can see now, you have a bunch of ripples here, and you have a bunch of ripples in the pass band. You can see the transition band is become very steep. Of course, as you start increasing the number of taps, the filter length will increase. The transition band start decreasing, so it starts becoming very 90 close to 90 degrees. You still have bunch of ripples here, and the processing time of course is going to increase because now you have more length of the filter. So each point has to be is going to take longer to be processed by that filter to yield the output filtered point basically. But the higher, basically the longer the filter length is, again the response become good, and when we treat this response with window function, as you will see, it becomes really good. Okay, so next topic is window function. We're gonna make another video.